Thank you very much for the introduction, Professor Slyankov. As you say, my name is Miguel Muñiz, and I'm developing my PhD in the University of Oviedo under the supervision of Professor Fernando Cantelli, and it's a pleasure for me to introduce you our work titled Joint Evaluation of Fracture Results from Distinct Test Conditions, Implying Loading, Specimen Size, and Geometry. This is the outline of my presentation. First of all, an introduction and motivation. After that, I'm going to introduce you the probabilistic model and an example of application taking into account the size effect with consideration of the probabilistic size effect and constraint size effect. Starting with the introduction and motivation, imagine that we want to obtain the critical value of a certain critical parameter as a material property. The first step is to solve this question: which is the parameter that defines the failure of the component? It could be a maximum stress, a zero stress, an equivalent stress, or maybe the stress intensity factor, plastic stress intensity factor, J integral, or any other parameter. We need to know what is this parameter. And the second example, and the second step is to perform an experimental program. If we are thinking in a deterministic way, we can make only one experiment and obtain the critical parameter. But as you know, we always have some scatter, so we must perform more than one experiment and feed our results and obtain the mean value, or better, obtain a relation between our generalized parameter or critical parameter and the probability of failure related with a Bayes equation. And it's important to notice that this relation, this curve, depends on the number of tests performed. On the other hand, in order to check the quality of our generalized parameter, we need to perform different experiments with different size or geometries and try to obtain the same primary curve. In other words, we need to ensure that our primary curve is size and shape independent in order to ensure that it's a material property. Here are some examples of experimental data with different size and geometries for SMB or compact tension. And here we have a problem because we usually have few specimens under the same test conditions. So the problem is, if we want to obtain a good reliability of the parameter selected, we must perform a lot of experiments with different size and geometries. But if we are thinking in a probabilistic curve, the reliability of this probabilistic curve depends on the number of experiments that we perform with the same condition. So we must choose. We can perform a lot of experiments with different test geometries and compare the results, or we must perform a lot of tests with the same geometries. But with the probabilistic model that I'm going to introduce you, we can evaluate different geometries and different size together as a whole and obtain only one primary failure distribution function with a good reliability. So we must not choose between these two alternatives. And this is the iterative process of the probabilistic model, and I'm going to introduce you each step. The first step obviously is go to the lab and perform some experiments and obtain the load and critical displacement, or TT/OD, in the test machine, for example, for 2 different or n different samples. After that, we need to simulate the results with a FEM model and obtain the distribution of our generalized parameter. This model is able to obtain the primary failure cumulative distribution function for any kind of failure parameter, and I'm going to use an example, the stress intensity factor. So we need to obtain the variability of the stress intensity factor along the crack front. And usually the next step in a probabilistic model is to sort in ascending order all the results according to the load obtained in the laboratory and assign to each a probability of failure according to a rank order formula. But here we have a problem, because each value obtained in the laboratory are related with a size. So we need to order all results in ascending order according to their probability of failure, but which one of these sample has the highest probability of failure? A small thickness subjected to a high value of critical parameter, or a big thickness subjected to a low value of the critical parameter. We need to solve this question before to go to the next step. We need to obtain the global probability of each component of it, or each sample with the Wakersling principle, taking into account what is the stress intensity factor along the crack front in each point. And we can sort of the results according to the global probability of failure, not according to the load applied. And it's important to note that in this step, in order to calculate the global probability of failure, we need to know what is the Weibull parameters, and we don't know what is its values at this point. So we can assume it randomly and start the iteration process to obtain good values. After that, obviously, we can use the rank order formula that I showed you before and obtain the probability of failure, real probability of failure for each component. But in this point, each probability of failure is still related with a size. So we need to transfer all results to the same size. For example, here we have the thin specimen and the thick specimen, and we want to put all results in the same scale in order to fit only one primary cumulative distribution function. So we need to transform our critical parameter, for example, our stress intensity factor, in an equivalent stress intensity factor according to this probabilistic formula, and put all the results in the same scale. And finally, we can obtain the Weibull values for all results together with a probabilistic paper or a MATLAB subroutine, and compare the Weibull values that we just calculate with the Weibull values that we assume in this point, and start an iteration process until the sum of this variation is less than a prescribed threshold. When this occurs, when this sum is less than a prescribed threshold, we can assume that our primary curve is a material property and allow us to obtain the probability of failure for any kind of geometries. We develop a software to do this automatically. The input values of our software are the critical parameter along the crack front, for example, the stress intensity factor along the crack front for different specimens. This is the main window of the software, and the output value is the primary failure cumulative distribution function and a prediction of the stress intensity factor for different thicknesses. And as you can see, there are a good agreement between the experimental results and the prediction. And I'm going to give you an example with real data. The objectives of this example of application are check the influence of the statistical size effect on the stress intensity factor, and check the influence of the aspect ratio in the probability of failure, what is influenced by the constraint effect, and compare the results with this methodology and the results obtained with the HTM standard. I use the data from Razum et al. That was performed 10 years ago, and I assume that homothetic specimens are influenced only by the statistical size effect. So between this experiment and this experiment, there are not influence of the constraint, because this is exactly the same geometry with a perfect scale. So maybe there are only scale effect, not constraint effect. We have more or less 8 experiments for each thickness and each aspect ratio. And starting with the first aspect ratio, we have here the experimental results for the stress intensity factor. And as you can see, there are the stress intensity factor decrease with the thickness, obviously. And we can put all the results in the same primary cumulative distribution function, and we can use this primary curve to predict the failure for different thicknesses and compare this prediction with the experimental results. The red curve is the prediction, and the black curve is the prediction assuming the coming value equal to 20 megapascals and in equal 4 that is stabilized by the HTM standard. We repeat the same procedure for each sample, and for every sample the stress intensity factor decreases with the thickness, obviously, but this influence is only for the statistical size effect. Here we can see the primary failure cumulative distribution function for each sample, and it's important to notice that M is more or less equal to 2.5, not 4, as the HTM standard defines, and K-mean varies from 24 to 45, not always equal to 20 megapascal. And the prediction of failure for different thicknesses are shown here, and the main conclusion of this are that HTM could be non-conservative in some cases, because they predict that this is the curve of 95% probability of failure, 50% and 5%. We usually use this to design, and in some cases the prediction by the norm or standard are not conservative with respect with the fitted data. And the comparison between the different samples should give us the influence of the constraint effect in the probability of failure. Here we have the comparison between the 5 samples. But nevertheless, the constraint influence exhibits contradictory or not congruent trends. This can be assigned to the inappropriate choice of the stress intensity factor as the reference parameter. So other options should be explored, because we cannot conclude anything with these graphs according to the influence of the constraint effect. And if we try to obtain the probability of failure for a sample based only on another aspect ratio, we obtain bad results. And this is because the stress intensity factor don't take into account the constraint effect. So we can use this, the stress intensity factor, to predict the failure for different scales when we maintain the aspect ratio constant. But if we change this, it's impossible to obtain any conclusion. So the conclusions of this work are that the proposed general local model allows a unique primary cumulative distribution function as a material property if we select in a good way the general parameter that defines the failure. The joint evaluation of all data from different samples as a whole ensures high reliability of the probabilistic assessment. And the methodology proposed proves the applicability without the generally regardless of the complexity of the failure criterion considered and the specimen size and geometry or law conditions applied in the experimental program. And our future work obviously is to test different failure criteria under different constraint conditions and determine with a probabilistic point of view which one could be the best, because the stress intensity factor obviously is not the best. Thank you very much for your attention.